Thank you, Edmund. I'm Jean-Laurent Philippe. I'm the director for HPC in EMEA for Intel. Thank you very much for inviting me. As Edmund said in the opening this morning, this roadmap update is with public information. Should you need or want to have more details about additional information about coming products, please don't hesitate to reach to Edmund or myself, and we'll be very happy to organize a specific meeting with you. I will be talking first about client CPUs with a focus on Alder Lake. That will be short. I will be spending a little bit more time on the server CPUs, a little bit on Ice Lake, the third generation Intel Xeon processor, because that is really something that is available at the moment until Sapphire Rapids comes later in the year. So this year we'll have two products. I'll give a lot of information about Ice Lake because it's already in production. But you can find even more publicly. We have already released a lot of information about Sapphire Rapids, and I will remind you of them. Then I'll go on to the discrete graphics accelerators, and typically those for the data center. I'll focus on Ponte Vecchio, and then I'll end with a short FPGA update. So let's go to the Alder Lake. What is important to realize is that we have two types of cores. We have the efficient cores and the performance cores. For the efficient cores, that means power efficient. The architecture is very specific, and it shows a deep front end, a wide back end, and of course, it's optimized for the latest transistor technologies so that it enables scalable multi-threaded performance for a modern multitasking. Very important to realize that it is optimized for power and density. That's really the idea for this type of core. And you can see here all of the various different pieces of ingredients that make it. I will not go to that level of details, but you can find already a lot of it here and online. Then we have the performance core. Here it is designed for speed, and speed means low latency and super high performance for single-threaded applications. So that means that here we will have a different approach, and we will have a very powerful vector engine and the new matrix engine, which is the evolution of AVX512 into AMX, Advanced Matrix Extensions. But that's not only those. There are a lot of other things that are happening. The goal is to really accelerate workloads. And for that, as I said, we have the new AI acceleration, typically the matrix engine, and a very smart new power management controller for fine-grained power budget management. That's how we balance the performance and still control the power. This will come into a processor which is called Alder Lake, and that will be a very scalable SoC architecture where there are various ingredients that are getting into it. It will serve all client segments and can range from 9 watts up to 125 watts. it is built on the Intel 7 process. It's completely new in terms of core design, and it is the first CPU that is supporting DDR5 and PCIe Gen 5 that you will see in some others. It also supports Thunderbolt 4 and Wi-Fi 6E. As I said, it is a modular design that can go from 9 to 125 watts, and it is composed of various building blocks: the performance core, the efficient cores, some of these here with PCIe controllers, display controllers, etc. The XE architecture with the execution units, different levels of cache and memory hierarchy in an SoC solution. And that will translate into some desktop CPUs that will have a certain number of P cores, certain number of E cores, some EUs from XE, and then mobile will have potentially less cores, maybe more graphics capabilities. Ultra mobile will also have potentially less cores, similar performance from the graphic interface. So really, all of this is becoming reality in the client side, and the P core that I'm showing here and that I talked about earlier with AMX will be also used in the coming Sapphire Rapids that I will talk about in a moment. But first, let's go from client to server CPUs and give some information and remind you of Ice Lake, what it is, what it brings, what's its performance, how it compares to competition. We introduced it in early 2021 as the third generation Intel Xeon Scalable processor, codename Ice Lake. The goal really is to, as usual, meet the demands of real-world application. Great to beat some world records, but what is important is what can end users and developers do with this processor. So as usual, Intel has been bringing a lot of new technologies in this new Xeon processor and has also enabled a lot of applications through the ecosystem collaboration that we work on. It is a new core architecture with a lot of I/O, more cores, etc. So I'll leave this slide for you to read later because it's a kind of reminder of what's in there, but I'll go into more details in the coming slides. What is important to remember is that there are more cores, like up to 40 cores. We have increased the IPC from the previous generation by about 20%, and we have larger L1 and L2 cache. We are bringing now 8 memory channels at 3200 with DDR4, up from 6 in the previous generation at 2933. With the Intel Optane persistent memory capabilities, you can put as much as 6 terabytes of memory per socket, so 12 terabytes in a dual socket platform, which gives a lot of memory to do a lot of things on large databases typically. Having more performance at the core level and more cores means that we need to have a much different I/O interface so that the balance is kept and that's not a bottleneck. So we have increased the number of PCIe lanes from 48 to 64 in this generation, and we have kept AVX512 and we have improved it from the previous generation Cascade Lake, and we have added some AI capabilities as well as other speed select technologies that I will talk about because it's very exciting and it gives a lot more flexibility on how to use more effectively and more efficiently in terms of performance, power, or cost these specific third generation Xeon processors. So second generation is the reference. And the third generation, you see that we have more cores. The L1, L2, and L3 cache have all been increased in size. Number of memory channels also, etc., etc. So everything has been bumped up in a way of making sure that there is no obvious bottleneck. This translates into a geomean of 50%-ish more performance over the previous generations. And you can see some sound bites everywhere here that expose some of the good things that are available. We are, of course, keeping the AVX512 from the previous generation, and we started with Skylake with AVX512. We have done a lot of work to enable some applications, and we keep on working with a lot of developers to make sure that AVX512 is bringing the level of performance that it promises. And therefore, we really encourage you to take advantage of this feature, which gives a lot of new performance for the application that have been enabled with it. We are bringing and keeping with Ice Lake the vector neural network instructions that are helping with inference mostly, and that is easy to use because the idea is we bring some instructions, we put them in the libraries. The libraries are called by the frameworks, and then they are automatically made available for the users. So it is very effective to use them. Just use the right upstream version of the frameworks. Speed select technology is providing 3 configurations of a CPU in a single CPU, which gives a lot of flexibility because it gives you active and nuanced control over the CPU performance. So let me give you a few examples of how it works. First, you can have the PP version of the speed select technology, the performance profile.
Sure. Yep. Apologies to interrupt, but maybe you need to turn off your camera because there's a lag on the slides, and multiple participants are experiencing that.
Oh, really? Okay. Let me try and do that. So that should work now.
Thank you.
Sorry for that. Thanks, Joachim. So what you can have is with a normal CPU that is not speed select capable, you will have a base frequency and a certain number of cores. And if you want to use less cores, then you will still run the at the guaranteed base frequency. What is interesting here is that as you decrease the number of cores, then the base frequency increases, and there are 3 profiles that are guaranteed by Intel. Unlike if you don't have speed select, you wouldn't be sure that there would be a base frequency speed bump if you lower the number of cores. So that's the first thing that is made available. The second one is the base frequency. You can decide that you want a certain number of cores to run at a lower frequency to allow the rest of the cores to run at a higher frequency. And that's because you might want to give priorities to those cores. You can also do something similar with the core power. You decide that a few cores will be allowed a little bit more power. Of course, as a consequence, some other cores will have less power. And then you can implement the application in a way that it will be using those cores. And finally, you can also control some of the turbo by allowing it to be going at a higher level depending on the number of cores. All this is available in the Ice Lake processor, and there is a document which is available that explains how to use it. You can use it easily, and typically this one here, you choose which profile you want, and that can be done either at boot time or even at runtime, which means that you could, if you would decide, to change without rebooting the profile. Say that you run an application that requires less cores and you want to be sure that you have the highest possible base frequency, then you would choose without rebooting to implement that profile. All this is resulting in 50-ish%, as I said, depending on which benchmark you use, performance increase over the previous generation of Xeon processors. And that's across various types of benchmarks, whatever they are, but in manufacturing, finance, energy, etc. That's great. How does it compare to competition? So here we are comparing the top SKU of Ice Lake, the 40-core 8380, to the top SKU of Milan, the 64-core 7763. And you can see that on various types of applications, and I'll stop here, we are seeing up to tens of percent of performance, which means that clearly you might remember something that we were saying some years ago, not cores are created equal. And this is true. The number of cores does not necessarily matter. With some applications, if all of the ecosystem enabling in terms of software development with the features that the Ice Lake processor is bringing are used, then you get an extremely high level of performance compared to competition. And for some applications that are more interested in terms of core count, here we are comparing a 32-core 8358 to 7543 AMD Milan. And you can see that on ANSYS Mechanical, for example, then we are seeing a performance benefit for the Ice Lake processor. So we have a winning, really great processor available today for your demanding applications. That's what we have in 2021. Now let's look at what's coming in 2022. next generation Xeon Sapphire Rapids that will come later this year. In addition to that, we will be bringing the Ponte GPU that will be available in the Aurora machine at the DOE in the US. Great, but that's not all. We are also bringing a version of Sapphire Rapid that will have HBM on the package. And as time goes in the future, there will be versions of all these swim lanes that will be evolving and that will be updated and increasing performance per watt, etc., and features. Why are we doing that? There are various types of workloads. Some are scalar, some are vector, matrix, spatial. But what we see typically is that in the workloads, there's usually a little bit of each. And that would be great if we could have a solution that would be kind of hybrid. And that's our idea of going into a solution that would be XPU, like GPU, CPU, IPU, VPU. That's what we are working on. And if we look further out in time, we could imagine that there would be on the package some, let's say, tiles that would be equipped with all of the 4 types of solution that I gave, some that would have more of 1 or 2 or even only 1 and little or no of the other. And that's what we are more and more looking forward to designing, that level of modularity and that capability of getting into solutions that are meeting the needs of some workloads. As we get into 22 and we get Sapphire Rapid and Ponte Vecchio, we are going on the scalar, vector, and matrix type of solutions and support for workloads. And the spatial version, I will talk about it later when I'm talking about FPGAs. So let's talk first about Sapphire Rapids. Sapphire Rapids is using the performance cores that I talked about earlier, and they implement the AMX, the Advanced Matrix Extensions. And they integrate a lot of acceleration engines, some that are for dynamic load balancing, some that are for data streaming acceleration, some for analytics extensions, name them, and also still the AVX512, still the other capabilities like quad, quick assist technology. So you will see that a lot is integrated and available when you need it. That's for the compute part. On the memory side, as I said, we are bringing DDR5 and the next generation of Optane persistent memory technology. We are also increasing the last level cache, some people call it L3, to north of 100 megabytes. And there will be versions of Sapphire Rapids that will include HBM. In order to serve all of these cores with such high performance memory, then we need to make sure that the I/O is at the right level. So we are moving from PCIe Gen 4 to PCIe Gen 5. And you remember that on Ice Lake, there were 64 lanes. We are going to 80. We are bringing the Compute Express link in order to connect over PCIe, and we are improving the multi-socket scaling with the UPI version 2. And of course, technology is used so that the 4, let's say, chiplets that you're seeing here are seen as logically monolithic, but they are multi-tile and they are connected through EMIB. As we go later into the year, we will bring a version of Sapphire Rapid that will have 4 stacks of HBM2E and up to 64 gig of HBM2E. That will significantly increase the memory bandwidth and therefore the performance of the application that are memory bandwidth bound. Now let's go to the other part of the data center updates, and let's focus on Ponte Vecchio, which will be working with Sapphire Rapids. Ponte Vecchio will have a lot of compute capabilities, and I will talk about them in a moment. Up to 128 ray tracing units, 128 XE cores, and I'll explain what a core is. And it will enable very, very high compute density at the socket and at the node level. A lot of compute capabilities. Again, we need to have a balanced solution, and there will be a lot of cache, L1, L2, and HBM2E also on the Ponte Vecchio. I/O is very important. Of course, we will use the PCIe Gen 5 that I talked about on the Sapphire Rapids. But in order for the GPUs to be able to work together without having to go through the CPUs, then we will have up to 8 links, XE links, that will enable full connectivity up to 8 GPUs. And again, the technology, EMIB, to make sure that we keep the level of tiling as a kind of monolithic view, and Foveros, which is the 3D stacking. There are a lot of tiles, as you can see, of different types on the Ponte Vecchio GPU, and they are made with different and the best manufacturing technology that each of them require, from Intel or from TSMC. Yeah, there are a lot of compute tiles, up to 47 compute tiles that are active and that make up to and a little bit north of 100 billion processors, as I said, manufactured on different process nodes. So what's the architecture of the Ponte Vecchio? It is based on cores that are aggregated in slices, themselves aggregated on stacks, and you can have up to 2 stacks on a package, and those stacks are connected with XE links. So let's start first with the base element, which is an XE core. The XE core consists of 8 vector engines plus 8 matrix engines. You notice that we call them XMX because they are slightly different from the AMX that you have heard me talk about on the Sapphire Rapids. Here, that's up to 4K bits in terms of registers, while on the Sapphire Rapids, it's up to 8,000 bits. But this means 512 bytes, and therefore we are capable of loading and storing in order to feed all of these matrix engines at the efficient speed. Then we aggregate 16 of these cores into a slice, and they each come with one ray tracing unit, and there's a total of one hardware context for all of these. And they come with 8 meg of L1 cache total. Then we aggregate 4 of these slices into a stack where we add the L2 cache that will be up to 204 megabytes. There is a media engine that is added, and there are 8 XE links that will be provided per stack. And then we put 2 of these stacks potentially to do a more high performance Ponte Vecchio solution. Therefore, Ponte Vecchio will be capable of being connected at the stack level by up to 8 links, and that means that you can get a fully connected 8 GPU on a node. We have announced earlier this year some performance results with the A0 silicon, and we have announced a little bit more than 45 teraflops of FP32 throughput. The memory fabric bandwidth measured at above 5 terabytes per second, and the connectivity bandwidth measured above 2 terabytes per second. So a lot of performance with a very well balanced solution in terms of I/O, memory, and compute. As usual, that's what Intel always provides. On top of this, of course, all this is part of the enablement done with one API that you've heard about and that you're hearing a lot about. And we are porting more and more applications to take advantage of the Ponte Vecchio features and capabilities. Finally, a few slides on FPGAs. We have the Agilex FPGAs that have been introduced and announced in the past with the idea and the target of providing much agility and flexibility. And similarly to what I talked about earlier, the Agilex FPGAs are very modular and can meet the needs of the end users, specifically depending on the various building blocks that the Agilex FPGAs are made of. They are providing very high performance compute, and they are manufactured on the Intel 10 nanometer process, which is called Intel 7. They are capable of memory coherent Intel Xeon processor acceleration, and that's a very interesting feature. They also show a massive bandwidth that is again helping with the high performance compute because you need to feed them. They are very easy to be integrated, and there are various tools for developing with them, including plans and work being done with one API environment. The first Agilex FPGAs are already shipping in production today. They have up to 2x better fabric performance per watt compared to competing 7 nanometers FPGAs. So that's very good because that's enabling flexible and energy efficient designs that can be used not only in the data center, but we are seeing more and more the FPGAs being used at the edge. They are also bringing a lot of features that allow to support very efficiently workloads, typically like the transition to 5G, the network cloud, and as I said, also the edge applications. So more and more we are seeing interest in the FPGAs, and especially as the environment for development is getting more and more user-friendly, there will be more and more interest and ease of use for those specific ingredients from Intel. In production today, we have the F series. It uses transceivers that are capable of up to 58 gig. They are based on the existing PCIe Gen 4, therefore they are usable with the third generation Xeon scalable processor Ice Lake based motherboards. They are using DDR4, so again, very well suited and aligned with the current generation of platforms. And they have an ARM A53 SoC option. Coming a little bit later this year, we have the I series that will be getting to the next level of performance and capabilities. And these are aligned with the PCIe Gen 5 solution, which is with Sapphire Rapids. It doubles the capability of the transceivers and seem still the same in terms of DDR4 memory and the quad-core ARM option. The one thing that they are bringing here is what is available with Sapphire Rapid, which is the coherent attach to the Xeon processor. Later in the year, and for even more compute-intensive applications, will be coming the M series that will be here offering an option to use not only DDR4, but also DDR5, which is about 50% higher bandwidth, as well as a support for the Optane persistent memory. And there will be an HBM option. As you know, once the data is in there, if it has to be, if it is a bottleneck for the application, if the application is memory bandwidth bound, then the HBM option will be capable of breaking that barrier and bringing the next level of performance at the FPGA level and at the platform level. With that, dear audience, I'm done. Thank you very much. And I'm 1 minute ahead of timing.
Yeah.